All right. So, good morning, everyone. I see in the chat you are already making yourself at home. It's nice to see. The circumstances are a bit different than usual. So we'll try this formula on stream on YouTube. We'll see if it works or not, if there are adjustments to be made. So maybe after this week, we could exchange some messages to see if you have some suggestions, if you'd like us to change something. We can discuss it in order to make the class better. Also, can you hear me well? Can you see me pretty good also? Is everything all right so far in the video format? All right, great. So first, I thought maybe we could just do a brief overview of the rest of the semester, what changes, what stays the same. First, we could take a look at the schedule. There were a few weeks that were cut off from the semester. We were supposed to have a total of 7 weeks. They were cut off to 6, in which we were asked to see about 5 weeks worth of material. So here is the schedule I was thinking of doing for the rest of the semester. In blue are periods during which we would have at least some theory, maybe not all of it, but at least some part. In red, the evaluations, such as here the exams. In white, pretty much everything else, time for you to work, revision time for the exams. And there are a few blank spaces because these are days we wouldn't have class. So this week we would continue our study of light, but in a different context than what we have done so far. Before we had studied it in terms of rays of light, so like you had probably done in high school, how they propagate whenever they change medium, using lenses, using mirrors, and so on. In this part, we would study light, but in a different manner, as we'll see in a few minutes. We'd finish that next week. And then the second exam would be on Monday in 2 weeks. So you can write that down in your schedule. It will be in approximately 2 weeks. Also, another evaluation which is not listed here is the two last labs, which were transformed into homeworks. The first one I'll send you tonight, which would be to hand in 2 weeks. And the very last one I would give you next week and would be to hand in 3 weeks. So you would also have 2 weeks in order to do it. Then in the other part, we would study modern physics. So a bit of quantum mechanics, a bit of nuclear physics, but at least for quantum mechanics, a lot less than we would have normally studied. We've got a bit, so we do not have a semester that is too loaded for what we can handle. Otherwise, I think everything else was sent to you by Mio. Yes, I think. On the schedule, would you have any questions? Something? Yes, all days are Sundays. It's just the first day of the week. It does not mean that Monday is April 26th. Just is the week which begins by April 26th. I made the assumption that weeks begin on a Sunday. Yeah. Yeah, the exam would be on April 27th. Exactly. Again, 2 hours, just like the others. Well, I will give you 2 hours, but it will be a bit shorter. I aim for about 15 minutes less than I would normally have given. The first lab will be this week. I'll send it to you tonight. The second one will be next week. There was also a pre-lab. I'll probably give it to you at the same time. It doesn't make any sense to hand it at the time of the lab since there is no real lab. So the first one this week, then the second one next week. Otherwise, uh, I think we'll be ready to start this week's material. Sorry, Paige, do we have to write the lab? No, well, the what will be to hand in for the two new labs will just be tables and calculations, no real lab report. It's really a focus on the analysis and the calculations, not really a lab with manipulations, aim, discussion, conclusions. Mainly the calculations. It will all be listed in the protocol. So for okay, for this week's material, if some of you checked out the video I sent to you, it's also in the study guide for this week, so it's not too late to take a look at it later on. The presenter Derek makes an experiment with people on the beach, in which he presents them a box with two very thin slits through which the light of the sun can penetrate. The light then goes into the box and goes and hit the backside of the box. And he asks the participants, before looking at them, what they expect to see in this kind of situation. So since I don't have the kind of material I can present to you in these conditions, I'll resort to simulations to represent what we will see. So I will have here on the left a light generator which act much like the sun would have in Derek's experiment. Then I'll place two very thin slits through which light will be able to pass. So once I push this button, light will be sent and will eventually go and hit these slits. And I will place on the right a screen which will be able to receive light that will go through the slits. What I'd ask you is take a few seconds to think about what you expect to see on the screen whenever light goes from the generator, passes through the slits, and hits the screen. You don't have to write it down in the chat if you don't want to, but at the very least, please try and think what you expect to see intuitively. This is important. In general, what we intuitively think would happen is if this is a light generator that emits light towards the right, we would expect the light to pass through each of the slits and produce one bright spot here, one other here for each of the two slits, and the other parts would be dark. Let us take a look at it. So the simulation kind of gives away the answer and the explanation. What we see in the end on the screen is not two bright fringes as we would probably expect if we imagined the light to just go through each of the two slits and go and hit the screen, but instead we get a bunch of bright fringes separated by dark fringes. Here we have three. We could think, well, we just have one more in the middle. If I change the wavelength of the light being emitted, we can have even more. Here we have a total of 5, and they are not even at the same positions the other were in the case of the green light. So, because of this, our treatment of light as a bunch of rays that go straight until they hit an obstacle, until they hit an object, an interface with another medium, is not sufficient to explain this phenomenon. We'll have to go back to the root of our study of light, in which we first introduced it at the very, very start of our study of optics as an electromagnetic wave. The fact that light travels like a wave is the key to explain this phenomenon. So, what we'll do for the rest of today's period, we'll first go back on the interference of waves in general, reintroduce the two cases we had talked about, constructive and destructive interference, and then apply these two cases to our study of light. So we'll try to explain why these fringes form by comparing it to what we said for the waves, and then put math on it. First in a general case, and then using the small angle approximation, which we first introduced in our study of the pendulum. This experiment, why it looks a bit stupid, was very, very important historically in the study of light, because how could I say? There were a lot of physicists which argued about the nature of light, whether it was a stream of particles or if it could be, by some chance, a wave. And this experiment was one of those which convinced the physicists that thought light was made of particles, that instead was a wave, because this pattern could not be interpreted if light traveled as a bunch of particles. So we'll go back to a system we know a bit better, meaning just waves in a medium, a mechanical wave. We had studied it in the case of sound wave as well as waves in a rope. We could also look at it with wave ripples on the surface of water. So here I have a pipe which lets out one droplet of water every few seconds, and the droplet that falls on the surface of the water creates outgoing wave fronts, here circular wave fronts. So like we had talked, you can imagine each blue part as being a maximum. So there is an outgoing sine or cosine function. This is a maximum, while the dark parts are a minimum. You can also take a look at it this way. So you have a maximum going to the right at the blue part, and a minimum going to the right where there is a dark part. And instead of having a single pipe dropping droplets of water, if we instead have two, I'll open the first one. Nothing new so far. It just sends out circular wave fronts outside from where the droplet hit the surface of the water. Now, if I hit the second one, and then the simulation is done so the two droplets are forced to hit the surface of the water at the very same time. If I send it, now the surface of the water is not agitated by a single wave produced by a single pipe, but is forced to oscillate by the superposition of the two. Remember, whenever we have a medium in which we have multiple waves, they add up to create a total wave. And the pattern we see here in the ripples of the water is the result of the addition of the two waves. There are a few interesting parts. So first, here in the middle part, we see very bright blue parts going to the right, and very, very dark black parts also going to the right. And we have weird parts over here, which seem kind of blurred. This is because they neither reach very far below nor very far above the cosine function. I'll just check it out here. This is in the middle. Just a second. Oh well, this is stuck in the middle. So over here we have a wave, a total wave that has a very high crest and a very deep trough, while here it always stays around zero. It doesn't reach very high up, doesn't reach very deep. So here is a case in which the two waves cancel each other to stay always at zero, while here we have a part in which the two waves added up to create a wave with a much bigger amplitude. Here we have constructive interference between the two waves, while here and here we have destructive interference, destroy each other to cancel each other. This is true for waves on the surface of the water. This is also true for other kinds of waves. Before we move on to these, so far, do we have some questions? As stated on the title of the stream, also, if you have a question that could take possibly a long time to write, you can just type in quickly question, and then I'll whenever I see this pop up in the chat, I'll wait for you to finish typing. If we, instead of having two pipes, we have two sources of light. It goes a bit faster because light travels faster than waves on the surface of water. What we said about waves on the surface of the water also holds true for the light. Since both are waves, they do not have a valid reason not to behave in the same way. So if, again, I have two sources of light emitting together, there will be zones in which they add up with constructive interference, other parts in which they will cancel because of destructive interference, and these alternate. We have constructive, destructive, constructive, destructive, constructive, destructive, and so on. We have an alternance of these phenomena. So here, this was due to two sources of light. In our first experiment, we didn't have really two sources, but a single one. However, this source of light emitted light towards the right, and then it hit two slits that were dug in an obstacle. Whenever light came and it hit those two slits. The two slits were the only part of the obstacle through which light could pass. So these two slits each act as a source. So they have this very same behavior as we had whenever we had two sources of light. This is our first source, and this is our second source. And through the addition of the two waves being emitted by these, we'll have a zone in which we have constructive interference, destructive, constructive, destructive, constructive, destructive, and so on. And if you take a look a little bit more to the right, here this was a constructive interference. If we go where the wave is heading, this is where we ended up with a bright fringe. Here we had destructive interference. And if we go towards the right, oh, we had dark fringe. Constructive, bright, destructive, dark. Whenever we had a bright fringe on the screen, it was light adding to itself because of the two slits. Whenever we had a dark fringe, it meant that light canceled itself through the action of the two slits. So this is not something we can intuitively conceive if we only worked with rays of light. We can only explain it if we treat light as a wave. So on the more intuitive part, using the animations, the applet, and so on. So far, are you alright? You have some questions? Does something seem not clear to you? Seems fine with Kimberly. Okay. The video I sent to you in advance talks a bit about this phenomenon, also about the original experiment behind it, designed by the British physicist Thomas Young. It's very interesting. If you have the chance to go to check it out, it's just 7 minutes long. It's very interesting. The channel Veritasium is one of my personal favorites whenever it comes to talking about science. So if you have the chance to go and look at it, please do so. So this phenomenon is called interference, to talk about the general destructive and constructive interference of the light with itself. Here, what we'll do. Yes, Jonathan knows it. Yes, it's very, very good. I love it. I absolutely love it. So what I suggest we do, we could take a look at the system we worked with, two slits and a screen with the intensity of the light, and talk about it using the waves we were working with, having the form of a cosine. So what I'll do, I'll switch over to this. So we'll start preparing ourselves to put math on this. So I have here the following physical things. I have two sources, and the two of them emit a sinusoidal wave towards the right. So this one I put in red, this one I put in blue to differentiate them. Also, I prepared, this could be useful, some distances, a wavelength of this wave. So here I'll just put this here. This distance when the wave is at 0 and is going up goes again at the same state. This is a wavelength. You could also see it by having it join two minima in the wave. So this is a wavelength, the distance it takes for the wave to go back on a similar state. And here I prepared half a wavelength. For instance, the distance it takes to go not from a minimum to another minimum, but to go from a maximum to a minimum. The two waves I prepared here have the same wavelength. This will enable us to have a better comparison with the scenario we studied, because in the scenario we took a look at, light all came from the same source initially, so the two slits should emit at the same wavelength, since the light came from the same source, which emitted a single one. I also prepared a guide to the eye, a certain position P, at which we'll take a look at how the waves behave. First, if I have two sources which are at the exact same position, so I'll just put the two sources on top of each other and look at some position P. Of course, since the two waves have the same wavelength and the two sources are at the very same place, if I look at point P, wherever I put it, whether I put it here, 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 the two waves always have the same sign, they have the exact same value. Thus, they will interfere constructively. They will always add up to create something larger. They will never cancel. So the result would look approximately like this. In black would be the result of the addition of the two waves. This also holds true if, instead of putting the two sources right on top of each other, I shift them by a specific distance. I'll shift S2 towards the right until I find another position at which I have perfect constructive interference. Here seems pretty good. So again, the result of the addition of these two waves would be a much larger wave. If I take a look at the distance by which I shifted the source, I shifted it towards the right by a distance of lambda, the wavelength. Again, if I move this source once more towards the right until I find another spot at which I have constructive interference, I once again moved it by another wavelength. So there are a few spots at which we'll have constructive interference between two waves emitted by two sources. If we take a look at the distance between point P and each of the two sources, this here is the distance between the second source and position P. This is the distance between the first source and, again, position P. And the difference between the two, if I take the total distance between the first source and position P minus the distance between the second source and point P, the difference is the distance between the two sources, here, two wavelengths. If I go back to the other case, the difference between this distance between the position P and the first source and the one between the second and position P is just this distance, a single wavelength. And in the very first case I studied, whenever they were right on top of each other, the difference between this distance between the first source and position P and this distance, the second source and position P, was a flat zero. They were the same place, so the difference between the two distances was zero. So whenever the difference that separates the position and the source between the two. Let me start again. Whenever what we'll call the path difference, so the difference between the two distances between each source and the position, differs by an integer times a wavelength, we will have a constructive interference in this case. Next, I'll try to find some cases at which I have instead a destructive interference. So I want the two waves to cancel each other. I'll try to find first position at which this happens. So I'll just put this right where I first took it and move it towards the right until I find again a position at which this occurs. So I want at every single position the two waves to cancel. This seems about right. So at every single position, so if I, just to guide your eye, you can look at position P. Here, the two waves have the exact same value, but with an opposite sign. This is true here, here as well, here both have 0, here, 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 and so on. And if I look at the difference between the two sources, this corresponds exactly to half of a wavelength. So whenever I place the two sources like this, and if I added up the two waves, I'd have something that is 0 everywhere. This is destructive interference. The two waves cancel each other. Once again, I'll try to find another position at which this happens. So I'll start again with this wave and move it towards the right until I find another position at which the two waves cancel. I'll begin my journey. Move towards the right. Here. And if I look at where I started and where I moved the second source, I moved by an additional distance equal to the wavelength of the wave. Again, at every position, the two waves always have an opposite sign, so they cancel, and the result will be a flat line, no wave at all. So we'll have destructive interference whenever whenever the difference between the two distances, so the difference between this distance that the first wave traveled from the first source towards position P, and this distance that the second wave traveled from its source towards position P, differs by half a wavelength plus some number of wavelengths. Here I added 1. I could also add a second one and still have destructive interference. So once they were shifted by half a wavelength, I can, from there, add an arbitrary number of wavelengths and still get destructive interference. Just using these two waves so far, is everything all right? Great. Please do not hesitate if something seems wrong. So we'll go back to this and apply it to the system we studied. The system we studied was not just two sources out in the wild. We had, I'll go in the hood, right? We had a system in which we had an obstacle, two slits. And in our little experiment, we saw that on a screen, we had bright spots and dark spots. So here I put a little graph of the intensity of the light. What it means is, here I put an axis with the intensity going to the left, and here is a curve of the intensity of the light as seen on the screen. What it means is whenever the intensity is high, so this location here is far away on the axis, this is a bright fringe. This is a place where we'd see a bright spot. And this location, which is at 0 on the origin on my intensity axis, is somewhere where the intensity of the light is 0. This is a dark fringe. And they alternate bright, dark, bright, dark, bright, dark, and so on. Each of these two slits, if we took them to be very, very narrow, we're able to see them each as a single source. This is linked to Huygens principle I introduced at the very beginning of our study of the light. It didn't work that well to explain it, but just look at it this way. These were the only 2 points at which light could go through. So each of them is similar to just having a flashlight, which would emit at a single wavelength. So here, I put the 2 sources in each of the slits. So whenever we see a bright spot on the screen, this means that the wave here, well, the wave as you saw in here simulation, that you saw here in the simulation went with circular wave fronts. So it emitted light in every direction around it. So it sent rays of light over in this direction, this direction, this direction, this direction. And so did this one, and sent light here, 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 here. And depending on where we look at the screen, a single ray from this one and a single ray from this one will go and hit this part of the screen. If we go back here, well, the present is just one ray, just one part of the wave that will start from each slit and hit the screen. I'll first take a look at the center of the screen, represented by the dotted line. Sorry, this is supposed to be over here. Okay. At the center of the screen, each of the 2 waves started from the source and went and hit the center of the screen. Since they are both equally spaced from the center, the distance, the wave that started from the first slit, that started here and went until it hit the center, is the very same distance as the one that started here, traveled to get over here. Both of them traveled in equal distance. This is the same case as we had before whenever we put the 2 sources right on top of each other. The 2 waves, whenever we took a look at position P, traveled the same distance. In the other bright fringes, I'll take, for example, this one, corresponds to, sorry, come on, there. To light starting from this slit, hitting here, and light starting from this slit and going to it at the same place. Now the 2 waves do not have to travel the same distance. Just by geometry, the distance that this wave travels to get right here is longer than the distance this one has to travel to start from here to here. So there is a difference between the 2 distances. But since we have a constructive interference, they differ by a value of 1 wavelength. The other bright fringe will be a case where the 2 distances differ by a factor of 2 wavelengths. Where is the? Here it is. So by 2 wavelengths. So this goes in here. The two waves differ by two wavelengths, and so on. And the same thing for the dark fringes. For the dark fringes, the only difference is instead of having constructive interference, we have destructive interference. So again, if I were to take this wave, send it over here, the first dark fringe above the center of the screen. Same thing with this one. Send it here. So this, since it is not in the center of the screen, the two waves did not travel the same distance. This one traveled a longer distance than this one, but the difference between the two is exactly equal to half of a wavelength of the two. And same thing, the other dark fringe over here is again a case where we have destructive interference. The two waves do not travel the same distance, but the path difference between the two differs by 1/2 of a wavelength plus another full wavelength, and so on for the others. This one will be half a wavelength, plus 2, and so on for the others. The same thing applies for the ones at the bottom. So this comes from the addition of the two waves being emitted by the two slits. So in order to continue, we have to put some math on it and do some geometry to find the equations we'll need to treat this phenomenon. Before we move on to this, so far, is everything all right for you? All right. Again, please don't hesitate if something is wrong. So I'll go back to the presentation I used at the start just to present the outline. I think I did. So I'll go back very, very shortly on what I just said, just putting some equations on it, putting some names, defining some symbols for interference of waves. Then we'll go and take a look at the case of light. And then the diffraction will be for tomorrow. It won't be for today. I just put it here for it to be already done. But today we'll focus on the first 2 points on the menu. So first, the interference. So I put here some diagrams. Also, the presentation I'll put up on Leah if you want to take a look at it. Just a PDF, so you can just take a look at it. It's not very heavy, not as much as video, so you can check it out. So I just put some more symbols on what we already discussed. So these are two of the cases we took a look at to introduce constructive interference. This is the first one in which we had the two sources at the very same place, and I named x1 the distance a wave has to travel to start from this source to go here, and x2 the distance a wave has to travel from its own source, s2, to go again to the same position, p. Here, the two distances are equal since the two sources are at the very same place. And at the bottom, I put the second case we studied in which the two sources were separated by a distance equal to the wavelength. So if we compare the distance x1 that the first wave had to travel, it is equal to x2, the distance the second wave had to travel, plus the wavelength of these waves. And from there, we can find the general relation. We moved the source toward the light more and more. So what we'll call the path difference between the two waves, meaning just the difference between the two distances they traveled, will be equal to an integer times the wavelength. So all these symbols will be defined just in a few minutes, literally with text on it. And the other case of destructive interference. So again, we took a look at whenever we had two sources separated by some distance, which made it so the two waves destroyed each other. I forgot to put x2. My bad. Sorry. It's very stupid. I forgot. Sorry. So x1 is the distance between S1 and P. X2 would have been the distance between this and this, so the distance the wave had to travel. They differ by half of wavelength. And then we could take S2 and switch it towards the right by the distance equal to the wavelength and still have destructive interference. So the condition we'll have here for the path difference between the two, meaning the difference between the two distances, will be half of a wavelength plus some integer time of wavelength, which I just rewrote as an integer plus 1/2, all of this times the wavelength. So this will be our condition to have destructive interference. And this is the definition with the two equations. So for constructive and destructive, delta in the path is the path difference in meters. M is an integer. It can be positive, negative, doesn't matter. And lambda is the wavelength. What we had in our system, we had the obstacle with the two slits, the screen which could gather the light, the dark fringes which were represented by having a low intensity of the light, and the bright fringe represented by having a high intensity of the light. So some geometry. We'll be eventually interested in finding the position of the fringes, whether they are bright or dark. So we'll have to find some equations just to represent where some point is located on the screen. Our point of reference will always be the center of the screen over here, which is represented by a dashed line. And if we want to look at some point on the screen, doesn't matter if it is bright or dark, just a general point here, which is represented by a black spot. We'll define a distance that it is from the center of the screen called y. And also, we will define, starting at the position of the slits and starting at the center, a dotted line that goes from this position up to where the point is on the screen. And we'll define an angle theta, which defines the orientation of this dotted line. Two other parameters we'll need in a few minutes. Well, the first one we'll need right away, the second really in a few minutes. First, the slits and the screen will be separated by some distance. In the video by Veritasium, this was the depth of the box. In a lab, it could be just the distance from the slits to the wall on which the light was projected, anything. And D, the distance which separates each of the two slits. This will have an importance later on. So just by geometry, with some general point of the screen and some general distance between the two, this is a 90-degree angle. So we can write the tangent of this angle by being y over L. Very general so far, no approximations. Next, we'll have to make an approximation to continue. We'll suppose that the distance between the slits and the screen, which we call L, is very large compared to any other quantity. Meaning it's very large compared to the distance with the slits D. It's very large compared to the wavelength. It's very large compared to every other distance in the system. If it is true, if the distance is very, very large, And we take a look at a dotted line that starts at each of the slits up until the point where it reaches our black dot on the screen. So the first one starts here at the top slit, goes over here. So I cut here with the three dots, continues and hit this point. The second one that starts here at the bottom slit, goes up, continues over here until it hits the point on the screen. If the screen is very, very far away, the lines do not have to be very inclined compared to each other. They will be approximately parallel. If the screen was close by, they would have to cross very quickly, so they would not be able to be parallel. But if it is very far away, they will tend to be parallel. This is an approximation. It is not exactly true, but still, it will enable us to find the main what I'm looking for, the main effects of what we will see. So we'll take them. If they're very far away, they will be approximately parallel. We'll do as if they were parallel. So if they are, and I compare to a horizontal dashed line in both cases, if they are parallel, they will have the same orientation. So the angle they make compared to an horizontal line will be the same. So I'll call both of them to be theta. By trigonometry, here I put a line which is perpendicular to this line and this line. So it has a 90-degree angle here, 90-degree angle over here as well. If I'll start at the top. If this is 90 degree, the angle between the horizontal line and this one is 90 degree minus theta. And since this between horizontal and vertical is 90 degrees, if this is 90 degree minus theta, this is 90 degree minus 90 degree minus theta. This is just the same angle theta. We find this angle here, here, and here. It is the very same one. We still have the distance between two slits, d. And if we take a look at the distance that each of the two waves had to travel to start from its slit and go to the point on the screen, they started at their respective slit, travel up until there. So travel some distance from here to here. And this one started here, travel here towards here. They do not travel the same distance, the bottom one, since I put the dot above the middle. The wave starting at the bottom slit has to travel a longer distance than the other. The difference between the two, if we take them to be parallel, is just this small distance over here. All the rest starting from here to here and here to here is approximately the same if they are approximately parallel. And so this very small distance is the path difference in our case, which is why I again use the symbol delta. Again, by geometry, here we have a 90-degree angle between this line and the other dashed line. I define them to be perpendicular to each other. So we have the sine of this angle, which is equal to delta over the hypotenuse d, which I wrote over here. Be very careful, this is only true if the screen is very far away. Otherwise, it is not. So we have these two equations so far. So I just rewrote them a bit. We had tangent equals something, sine equals something. I just isolated some of the symbols. So we have delta, the path difference between the two, d, the distance between the two slits, y, the distance between the center and the point on the screen, l, the distance between slits and the screen, and theta, the angle, which tells you where the point is located on the screen. compared to the center. So these are the two general equations we'll work with, at least in general. But for the path difference, we took a look at two very specific cases, one in which we had a constructive interference, meaning a bright fringe, and the other in which we had a destructive interference, meaning a dark fringe. So we'll go back to our definition of these two types of interference. We have at the bottom the equation for constructive interference in terms of path difference and wavelength, which we said the path difference, the difference between the two distances traveled, has to be equal to integer times the wavelength. And this integer at the center, since they both travel the same distance, is a flat 0. At the top, it is 1. So 1 wavelength difference. This one is 2 wavelengths. And at the bottom, it is -1, -2. Sorry, it should be a -2. I'm very sorry. It should be -2. I'll correct it whenever I send it to you. My bad. So they can take negative value. This also holds true. This was written in the other slide. I forgot to mention it. Whenever we define y to be the position of a point on the screen, if it is above the screen, we'll take it as positive, but it can also be negative if it is below. So we can very well have a negative y, a negative theta, a negative m. It is allowed. In fact, it is even required. So this is for constructive interference, which explains the bright fringes. And we have the dark fringes, which were explained by the destructive interference. Again, we have our condition. Now, for the dark fringes, there's a trap. If we take a look at where we had some dark fringes, we didn't have one in the middle, since the middle had to be a bright fringe. The two waves travel the same distance. They have to interfere constructively. If we start from this expression and we try a few values for m, this has to be an integer. So if we put 0, we have a path difference of 1/2 times the wavelength. So the first dark fringe above the center is not for m equal 1, but m equal 0. Over here, it is for m equals 0. The second one is for m equal 1. The third one for m equal 2. And at the bottom, if we put negative values of m, so here I started at 0. If I put -1, I'll have -1 plus 1/2 minus 1/2 times the wavelength. So the first dark fringe below the center is for m equal -1, then the other one -2, and so on. The values of m for bright and dark fringes is often referred in the exercises as the order of a fringe. So whenever you are told in the exercises that you are looking at the fringe of order 2, for instance, this means that the index of m will be equal to 2. However, they might sometimes tell you that you're looking at, for instance, the third bright fringe above the center. If it is for a bright fringe, all right, the third bright fringe, m equal to 3. However, they tell you instead that you're looking at the third dark fringe. The third dark fringe has a value of m not of 3, but of 2 instead. So be careful around this. The volume sometimes tries to trap you. Be careful. So from these two conditions, we can combine it with our equations we had before. Each of these two expressions, this one for destructive, this one for constructive, you can put them in your equations. This delta is the very same as the ones in the two expressions. So you can use a general method by combining these two equations, knowing the two angles are the same, to find the position of the fringe, the distance between the slits, the distance between the screen and the slit, and so on, by combining these equations. If the angle we're looking at, so the angle between the center and somewhere we're looking at, is small, we can make further development in our expressions. The conditions we discussed whenever we study the pendulum stays true. We can approximate an angle to be small whenever it is smaller than 10 degrees. Again, this is an approximation. We can never, what we'll discuss is never exactly true, but it is not so bad if the angle is below 10 degrees, and it gradually gets worse and worse. So if we have a small angle, we discussed in the pendulum that the sine of an angle was equal to the angle itself, but also we can demonstrate using that the tangent is a sine over a cosine that it is also true for a tangent. The tangent will be also approximately equal to the angle, so both will be approximately equal. And in our two equations, we had one with a tangent and one with a sine function. So if our angle is small enough, we can say that the two expressions are approximately equal. The tangent is approximately equal to the sine. This has to be approximately equal to this. We can put the two of them equal, and from there find an equation of some position on the screen compared to the path difference, the distance between the slits and the screen, and the distance between the two slits. And this, in the case where we have constructive interference, where we're looking at a bright fringe, we can replace with m lambda. And if we look at the dark fringe, meaning we have destructive interference, this we can replace by its expression. So we have an expression of the position of the bright fringe of order m, and here we have an expression of the dark fringe of order m also. So these expressions tell you the position of the bright and dark fringes in the small angle approximation created by a system in which we have distance L between the slits and the screen, and a distance D between the two slits. And we can see from this expression, the positions will depend on all these parameters, D, L, as well as the wavelength being sent in the system. So before we move on to just go back on our intuition, see how these equations translate into our physical system we took a look at the beginning. Would you have questions so far? We don't have very long to go. So what I'll do, go back here. So if we represent our parameters in the system we took a look at in the beginning, the distance from here to here is D. The distance from here to here is L. And the wavelength is indicated here, well, through the frequency. If I change the frequency, I also change the wavelength of what I'm sending. So here I'm sending violet light towards the screen with some distance. First, while I'll vary the wavelength first. So here I have one bright fringe, another, and another here. If I change the wavelength, so keep your eyes on the position at which we had bright fringes. If I go back to green light, the position are in the same place. I do not even have the same number of bright fringes. If I go to red light, they are not in the same place. We always have a bright fringe in the middle, since no matter what wavelength we send, we will always travel the same path here and interpret constructively. The others change a bit. The red light has a larger wavelength than green, and green has a larger wavelength than violet. The larger the wavelength, the more the bright fringe, here like the first one, the more the bright fringes move outwards. Here it is approximately here for violet. Keep in mind the first red one was here for violet. The first one is more towards the center. So the position of the fringes goes more outwards the greater the wavelength. This corresponds to what we discussed. The greater the wavelength, the greater the value of y. This will also change depending on the distance between the two slits. I'll go to green since it is very visible. And I'll change the distance between the two slits. Here I put it, here I put it to be 1,500 nanometers. If I make it smaller, so at first there will be some distortion since the wave will continue to advance, but I'll change the system. So just give it a few seconds to calm down. If I bring the two slits closer, gets a little bit weird. I'll put a bit more of a distance. So we have the central bright fringe, the first one at the top, the first one at the bottom, and they are farther apart than they were in the other case. If I separate more the two slits, again, first we had the first bright fringe over here. If instead I put the slits much farther apart, where I had the first bright fringe in the other case, here I have, this is the center, first, second, and I was even a little bit more outwards than in that case. So the first bright fringe, which was here, moved to more toward the center. And to do this, I increase the distance, I increase the whenever these increased, so whenever the slits are further apart, y diminishes. The position of the bright fringe will be more towards the inside. The same principle applies to the dark fringes. I just focused on the bright fringes since they were easier to see. And I used the expression for the small angle approximation to discuss this. This also holds true if I were to use the general case. It's just a bit harder to see. In the small angle approximation, we have a very nice ratio we can work with, so it's a bit easier to build our intuition. Questions, comments on this? Something you think I forgot? Something that wasn't clear enough? Yeah. because that will be the end for today. Otherwise. Well, I'm not really equipped to do examples live, so I was thinking more of sending you to check out these examples, and so yeah, I'd focus more classes to explain the theory. So really, these I wouldn't do online. It's basically the first one you can check out in your textbook. The other two are deposited on there. They're already solved. It's really for science, more for you to check them out. You can try them before looking at the solution, but I saw it more as outside of the class since right now, at the very least, I always have the equipment to switch between a few different uh, cases. Yes, Kimberly. Basically, I sent the updated version of the study guide yesterday. You can do about every exercise I listed in there. So all the exercises were in chapter 35. So the theory we saw today is everything we can do problems on for chapter 35. So you can begin right away. And Catherine, yes, I suggest you take a look at the study guide. I cut some material. Eventually, we would have studied thin films also. So maybe I'll mention them just briefly, qualitatively, just in a few sentences next week. I'll see. But I cut off everything about thin films. Every problems, we won't solve anything about them. It's really the core of chapter 35 was the study of light as a wave and its implications. And we build on this in chapter 36. Eventually, when I get a second camera, I'll probably be able to do something else. Otherwise, I'm kind of stuck right now. But yeah, as I said, we'll try it this way this week. At the end of the week, we can discuss how it went, what should be improved, and then we'll try to build on it. Yeah, so everything I mentioned is on there. The study guide, the examples, everything is on there. There is a section additional solved exercises. So whenever I talk about the solved exercises in there, this refers to this section on there. Any other questions? Oh yeah, right. So sorry. Yeah, Charlene. Thank you. Yeah, I asked you through me if you would agree to do tomorrow's class, which will be yeah. So it's not very long. Would you agree to do it at at 1 p.m. instead of 5? I got an answer from about 3 people. So the rest of you that are here that did not answer yet, would you agree to move the class at 1? Okay, so I'll ask directly. I'll send an email directly to. Okay, cool. I think there's one person that didn't answer yet so far. So if I combine both the chat and the mails that were sent to me, so I'll try to contact the last person, and once I have their approval, I'll send the confirmation from you. But I'd like to do the class at 1 if possible. Any other questions before I end today's class? Otherwise, don't hesitate to send them to me through Mio on the forum. I'll also be available at the usual time. Like I'll be available today at 11 on Zoom. Like I said in the message I sent you. So don't hesitate to drop by. Otherwise, I'll see you tomorrow.